All right, so we're looking at Chapter 9, Section 9.2, testing claims about proportions. So after today, we should be able to state and check the random 10% and large counts conditions for performing a significance test about a population proportion, calculate the standardized test statistic and p-value for a test about a population proportion, and perform a significance test about population proportion. And lastly, interpret the power of a significance test and describe what factors affect the power of a test. So starting off the conditions, this should be very similar to our confidence interval conditions. So we should be pretty used to them by now, but the three are random. So the data comes from a random sample from the population of interest. And then the second one was 10%. So when sampling without replacement, our sample has to be less than 10% of the size of the population. And our last condition are large counts that both n times p naught and n times 1 minus p naught are at least 10. So because we assume h naught is true when performing a significance test, we use the parameter value specified by the null hypothesis p naught when checking the large counts. So we use p naught because we assume p naught is true, and we're going to use that for our calculation. So that's why we always will use p naught here. For a test, use null value p naught, not the sample portion p hat, to check the large counts condition. So that's a slightly difference from confidence intervals to hypothesis testing. So remember, now we're looking at n times p naught and n times 1 minus p naught to be at least 10. So looking at an example, according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. She would like to carry out a test at the alpha of 0.05 significance level of our null hypothesis, which is p is equal to 0.25, and our alternate hypothesis, which is p is less than 0.25, where p is the true proportion of all students at the school who have a part-time job. So realize that it should be done, that our alpha level has been stated before we've done any calculations whatsoever. So we're good there. The administrator selects a random sample of 200 students from her school and finds that 39 of them have a part-time job. So let's check the conditions for performing the significance. Right off the bat, first one is random. It tells us that a random sample of 200 students from the high school. So we're good there. Random, it could say a random sample, random assignment if it's an experiment, or an SRS, a simple random sample. Those all kind of qualify for random. For the 10% condition, we're going to use the fact that our sample size, which is 200, is less than 10% of students at a large high school. And large counts, we are going to use n times p naught, or which is 200 times 0.25, which is 50, which is greater than 10, and the probability of failures, or the number of failures, n times 1 minus p naught, is 150, which is also larger than 10. So we're good with the large counts. And again, realizing that, hey, we are looking at p naught, not p hat. So looking back, if you remember from the book or from the last video about the basketball player who claims to be an 80% free throw shooter, and we thought they were exaggerating. So remember, our null hypothesis is p is equal to 0.8, and our alternate was p is equal to, or p is less than 0.8. So if h naught is true, so we're assuming that p is equal to 0.8, then what would we expect for p hat to be if we took a random sample? Well, if p is true, then we'd expect our p hat to be pretty close to that p. And so also thinking about where do those kind of conditions fall into it, and kind of why that they're important. So we can talk about the shape of the distribution, and because of the large counts, or that n times p naught and n times 1 minus p naught, it tells us that this sampling distribution of p hat will be approximately normal. For the center, we're assuming p to be true. We're assuming p naught is equal to 0.08. So we are going to use that as our center for our sample. And then our variability is very similar to the standard deviation, which is going to be p naught times 1 minus p naught all over n, take the square root of that. Well, the reason why we can use this formula is because we've met that 10% condition. So the 10% condition is true, which allows us to use this formula. So the question is, well, what should we expect our p hat to be? If you remember from that problem, we saw that the player made 32 out of 50 shots, or a p hat value of 0.64. So the fact that we're assuming p to be 0.8, our mean to be 0.8, 0.64 is pretty far away. And so we can find out how far it is or how many standard deviations it is away by taking the z-score or the standard from the standard normal curve. And we do that by using this formula, p hat minus p naught all over what was, quote unquote, the standard deviation, to get that it is negative 2.83 z-scores away from it, from the mean. So we're pretty far away from the mean right now. And we say that the value z is negative 2.83, and we call that the standardized test statistic. That should be a little bit familiar, maybe from earlier in the year in first semester, finding those z values. We typically found them with means. Now we're looking at it with our proportions a little bit. So the standardized test statistic, that measures how far a sample statistic is from what we would expect if the null hypothesis were true. So it's basically how many standard deviations it is away from the mean. So in this case, 0.64, it's about 2.83 standard deviations less than the mean. All right, so we find that z-score by doing the statistic minus the parameter divided by the standard deviation of the statistic. So the left-hand side is if we were finding the normal distribution of our mean is 0.8 and our standard deviation of 0.0566. The right-hand side, they look very similar. The only difference is what the mean is and what the standard deviation is. So the z-score is the standard normal curve. It's what we use our table from, and it has a mean of 0 and a standard deviation of 1. And so it's how we can kind of compare any z-score or any p hat and p and standard deviation. We would compare it back to the normal curve. We've basically taken that p hat and turned it into a z-score or a value that would have been found on the standard normal curve. So if we want to find the probability of getting a value of 0.64 or less than in that basketball shooting example, you could use the calculator to do this upper should be if I was doing it for the basketball problem, I would do normal CDF, lower 1,000, upper 0.64, and then my mean 0.8, my standard deviation 0.05, or whatever the standard deviation was, to calculate out and get my z's, get the probability of getting a value that small or less than. You could also use the table, and I'll show you how to use that table. But if we want to use the table, we have to find our z-score. So we get our z-score to be negative 2.83. So then we go to our table, we find the z-score negative 2.83. So I'm going to find negative 2.8, and I'm going to scroll over on that table until I get to 0.3, which would be here. And I see it's 0.0023. So the column and the top row is the z-score. Inside the table is the probability of getting that z-score or less than. So you can see it here in this value. Here is our z-score. And so the value in the table is anything from negative infinity up until hitting that z-score. So this is a negative z-score table. This is the positive z-score table. So we can see that it's still going from negative infinity up until that z-score. So maybe if you want to find what's the probability of this value and greater than, well, you'd go to the table take whatever value it was and then take 1 minus it to find out this white part of this graph if you want to find it greater than. Or you could just use technology to do it. But either option is fine. All right, so let's look at another example. In the preceding example, an administrator at the school was looking at if more than or if less than 25% of the kids had a job and they're using an alpha level of 0.05. So the sample 200 students found 39 of them had a part-time job. So it says we're going to find 3 things. So explain why the sample results give some evidence for the alternate hypothesis. Well, if you just straight up did p hat, which is 39 out of 200, you get a p hat to be 1.195, which is less than 0.25. So you're like, okay, well that gives me some pretty good evidence that hey, it is less than, so I'm in a good shape. But the question is how much, how strong is that evidence? The same idea as our confidence interval when we would use our p hat as our point estimate, and then we want to be like, well, how much would it vary, or how likely is this to actually be that value? We want to do more than just find our p hat. So we're going to do our confidence interval, or we're going to take we're going to find the probability of getting that p hat and or something less than it. So they said part B was to calculate the standardized test statistic, which is called the z-score. And so to find that, I take my statistic, which was 0.195, minus the mean, which is 0.25, divided by the standard deviation of p hat, which is here, and I get a z-score of negative 1.8. To find the p-value then, I want to find what's the probability of getting negative 1.8 or less than. So I could use a table and I look for the z-score negative 1.28 or negative 1.8. Or I could put it into my calculator. That 2 should be a negative sign. Just so you know, it should be lower negative 1,000 to upper negative 1.8. Mean is 0, standard deviation is 1. And I get that. Or you don't have, yeah. And you could see that probabilities here. You technically could also, you should get the same answer if you didn't normalize it. But in this case, we are now getting to the point where we want to and have to show that step of normalizing it and getting my z-score out. So we do want to use lower negative 1,000, upper whatever the z-score is, negative 1.8, mean 0, standard deviation is 1. So when we did that, we found that the probability of getting a value of, or 39 out of 200 students or less than, is 0.0359. So it occurs 3.5% of it. So we should have seen kind of this conclusion be made from 9.1. But it says since the p-value is 0.0359 is less than alpha, which is 0.05, we reject HO. And since we reject HO, we have convincing evidence that the true proportion of all students at this large high school who work a part-time job is less than 0.25. So we reject HO, we have convincing evidence in favor of the alternate hypothesis, which was less than 0.25. So we are now going to be looking at our one sample z-test for P. So this is it's very similar. You'll see some overlaps between the one sample z interval for P, where we took a confidence interval. Now we're actually doing a test for z. So we're going to have the same 4 steps: state the state, plan, do, conclude, except what we have to do in each one is a little bit different. So here for our state, we need to state the hypothesis you want to test and the significance level, and define your parameter. You need to plan. You need to identify the appropriate inference method and check those 3 conditions. Do, we want to give the sample statistic, calculate the standardized test statistic, and find the p-value. And then finally, conclude. Make a conclusion about the hypothesis in context of the problem. So where do the three conditions come and why are they important? The random condition. The fact that we need this to be a random sample, because the whole idea is that p hat is we'd expect it, if it was a truly random sample, for it to be pretty close to p naught. We're assuming p naught to be true, and so if we're going to use p hat, we would want it to be kind of a pretty good estimate of it. So we need a random condition to ensure that it is a pretty good estimate for p naught. Number two, the large counts condition. The large counts condition, which is n times p naught, is larger than 10, and n times 1 minus p naught is larger than 10. If those are met, then we say that this distribution is approximately normal. And since it's approximately normal, we are then able to use a normal curve, and more specifically, we're able to find and standardize our test statistics. So we're able to find z because our sampling distribution is approximately normal. And the third condition is the 10% condition, which allows us to use that formula that we've seen quite a few times about the standard deviation of, we saw it for p hat, now we're using it with p naught times 1 minus p naught divided by n. And we can use that because of the 10% condition. It says that the sample is less than 10% of the full population. So it doesn't change the actual population that much when you're sampling without replacement. So we're able to use this formula because of it. All right. So these are just kind of the different tests we might do based on our hypothesis. So our null hypothesis is always p is equal to blank, whatever it's going to be. P is equal to p naught. So maybe p was equal to 0.8 in that basketball shooting example. The alternative hypothesis is dependent on what the question's asking. So if we thought that it's actually larger than p naught, then we'll do a one-sided test for greater than. If we think that that person was exaggerating their basketball score, we think it's less than 0.08, then we would do a one-sided less than test. And if we don't really care if it's less than or greater than, we just think that it's different. If we think there's a difference in what that p naught is, then we would do a two-sided test. So let's look at an example of a one-sided test. So from yesterday, not yesterday, but from 9.1, we talked about potatoes and how depending on if the sample was more than 8% of potatoes had blemishes, then the truck would be sent away. Otherwise, you would accept it. So a specific example, the supervisor selects a random sample of 500 potatoes from a truck, and inspector reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the alpha of 0.1 that more than 8% of the potatoes in the shipment have blemishes? Well, first things first, we have to do our state. State our null hypothesis, p is equal to 0.08. Our alternate hypothesis is p is greater than 0.08. And then state what you're actually doing, or state what the parameter is, which is p, the true proportion of potatoes in the shipment with blemishes, and we're using an alpha level of 0.1. For the plan, we're name the test a one sample z test for p, and then our three conditions. So random samples of 500 a random sample of 500 potatoes from the shipment. The 10%, it's reasonable to assume that 500 is less than 10% of all potatoes in the shipment. So the shipment's going to have more than 5,000 potatoes. And the large counts, which is 500 times p naught, which is 0.08, is equal to 40, which is bigger than 10. And 500 times 0.92 is equal to 460, which is bigger than 10. So my three conditions have been met, so I'm good to continue on to the do phase. Quick note, if at any point the condition is not met, you stop right there. You can't continue on if the conditions are not met. But since they we're good to keep going. So we're going to do the do phase, which is 47 divided by 500. Find that we get this sample was 0.094. So right off the bat, right, with that p hat, it's like, okay, well, we're trying to see, we think that it's more than 0.08. And right off the bat, we do have some evidence to suggest it because 0.094 is bigger than 0.08. But how strong is that evidence? So that's what this test is actually going to do. So we take our z-score to get it to be 1.15. And then we use our table or the calculator. So we find what's the probability of getting a value of 1.5 or greater than, and we see that it is 0.1251. So basically what this means is saying the probability of getting a value of 1.15 or greater than by chance alone, knowing that the true proportion is 0.08, is 12% or 12.5%. Okay. And 12.5%, that's pretty common. That could happen pretty often. So because our p-value is larger than our alpha, which is 0.1, we fail to reject HO. Basically, we do not have convincing evidence that the true proportion of blemished potatoes in the shipment is greater than 0.08. So we do not have convincing evidence of the alternative hypothesis. Some tips here. So always make sure that if you fail to reject your H naught, remember your kind of conditions. You either reject HO or you fail to reject HO. We never have evidence to support HO. It's either reject it or fail to reject it. But just be sure to interpret the results as we do not have convincing evidence for HA if we fail to reject HO. So if you fail to reject HO, then we always follow it up with we do not have convincing evidence for HA and state what HA is in context. Another tip also, don't abbreviate things. So fail to reject, just write fail to reject. Don't abbreviate things. Another tip, you can use the calculator to carry out your mechanics of the significance test on the exam, which is what I was saying. You could put this in to your calculator to get that p-value, but you don't want to go right to it because you might skip some steps or you might not show everything you have to. So in that do phase, remember I showed my p-value. Let me go back. I show my p-hat, I show my z-score and how the formula I used to calculate it got my value, and then went into it. And that's when I use either technology or the table. I don't want to just take this and jump right into the technology. I need to show all those steps to get full credit. Next thing, what about a two-sided test? So the p-value in a one-sided test for a proportion is the area in the one tail of a standard normal distribution. So it was p was greater than, I shade to the right, p is less than, I shade to the left. And a two-sided test is, I don't care if it's less than or equal or greater than, I just want it to be, it's not equal to it. So it can be in either direction, greater than or less than. So let's see a problem with this. So the Center for Disease Control and Prevention said that 68% of high school students have never smoked a cigarette. Yang-Ho wonders whether the national results holds true in her large urban high school. So they take a random sample of 150 students from her school. She gets a response from all of them and find that 90 say that they have never smoked a cigarette. Is there convincing evidence that the CDC's claim does not hold true? So we have to do, if they're asked a question, you have to go through the whole steps for a hypothesis testing. State, plan, do, conclude. So I state my conditions. P is equal to 0.68. My alternative, P is not equal to 0.68, because I'm just seeing, is it true or not? I don't care if it's less than or greater than. I want to see, is it true? Yes or no. So I can use both directions. In here, so I'm using a two-sided test, and I use where P is equal to the proportion of all students at the school who have never smoked a cigarette, and I'm using my alpha value to be 0.05. My plan, one sample z-test for P, and I have random 10% large counts. Remember, for the large counts, I'm using P naught, so I'm using 0.68 there. I do all this before I even look at P hat. So I get my state plan before I even do my P hat. The do is when I finally take this P hat to be 90 divided by 150 is equal to 0.6. I can use the standardize, I can standardize this score, take 0.6 minus the of P naught divided by the standard deviation, get a z-score of negative 2.10. So remember, negative 2.10 is here, but I also want the other side as well. So it could be negative 2.1 or positive 2.1. So you could do two separate calculations, or since you know that the normal curve is symmetric, if I can find this probability, and if I'm 2.1 to the left, it's going to be the same probability if I was 2.1 to the right. So I can find these two probabilities, or I can find one probability and just double it. So I'm going to use the table to find what's the probability that it's less than negative 2.1. That's 0.0179, and I'll double it so I can count for both probabilities here. You could also do it in your calculator. Either one is fine. And then I'll conclude. Because our p-value of blank is less than alpha, we reject our H naught. So since we reject our H naught, we have convincing evidence that the proportion of all students at Younghan's school who would say they've never smoked a cigarette differs from the CDC claim of 0.68. So basically, we have convincing evidence that there's a difference, that this sample has actually produced something different for their school's population than what the CDC claims. Another tip, when you're using the conclude statement, when you're actually writing about it, you're talking about the parameter, not the statistic. And that's right up the same alley as those confidence intervals that we talked about. So just a link between kind of a confidence interval. It's more so linked to the two-sided test, right? Because in a 95% interval gives an appropriate set of p naughts that should not be rejected by a two-sided test at the alpha level of 0.05. So a two-sided test at a significance level alpha and a 100% of 1 minus alpha percent confidence interval. So basically a 95% confidence interval if alpha is 0.05. All right, so we're now looking at the power of a test. We kind of saw this a little bit in 9.1. We saw that the probability of making a type 1 error was our alpha value. And so the power is a little bit linked to the probability of making a type 2 error. So just as a reminder, a type 2 error occurs when the null hypothesis, in reality, the null hypothesis is false, but we fail to reject it. So we don't have convincing evidence against it. So we fail to reject it when in reality we really should have rejected it. Okay, so that's when it occurs. So the idea of power is how likely is a significance test to avoid a type 2 error. So the definition of power is the power of a test is a probability that the test will find convincing evidence for HA when a specific alternative value of a parameter is true. So let's look at an example. Let's return to that idea of those AAA batteries. So we saw that regular AAA batteries had lasted for 30 hours on continuous usage on average. The company plans on selecting an SRS of 50 deluxe AAA batteries and use them continuously until they completely drain. Then it will perform a test at the alpha level of 0.05 with those hypotheses where mu is the true mean lifetime in hours of the deluxe AAA batteries. The new batteries are more expensive to produce, so the company would likely be convinced that they really do last longer. The power of a test to detect that mu is equal to 31 hours is 0.762. So they're telling us right now the power or the probability that the test finds convincing evidence against HA when a specific alternative value of the parameter is true would be 0.762. So we interpret power as a true mean lifetime in the company's deluxe AAA batteries is 31 hours. There's a 0.76 probability that the company will find convincing evidence for HA, which is the mu is greater than 30. So basically, in that idea, we use the idea of, or in that last example, we used the idea of given statements. So the probability that we reject H naught given that mu is equal to 30. So mu is 0.76, or that's what the power is equal to. So a type 2 error occurs when the null hypothesis is false, but we fail to reject. So here, the probability that we fail to reject, given that mu is equal to 31. So you see how these are complements of each other. So it is equal to 1 minus that probability, or 0.238. So in this example, the probability of making a type 2 error is equal to 0.238 because the power is 0.762. So this formula is pretty important to kind of realize. Power is equal to 1 minus the probability of a type 2 error. Or if you want to find the probability of a type 2 error, it's 1 minus the power. So what can we do to decrease the probability of making a type 2 error and increase the power of a test, right? Because the larger the power, the lower the type 2 error would occur. So to increase the power of a significance test, the power of significance test to detect an alternative value of the parameter when H naught is false and HA is true, based on random samples of size n and significance level alpha, will be larger when the sample size is larger. So the significance level of alpha is larger, and the null and alternative parameter values are farther apart. Okay. So the power of a significance test with a size n and significance level alpha will be larger. So to increase our power, decrease the type 2 error. If we can increase our sample size, have a larger alpha level, which we saw yesterday. We saw that increase alpha increases probability of type 1 error, decreases probability of type 2 error, or the null hypothesis and the parameter. The null hypothesis and alternative are farther apart. So a quick example, looking at Alzheimer's experiment, want to test a drug that fewer than 10% of patients who take the new drug for treating Alzheimer's disease will experience nausea. That is that they want to carry out a test of H naught where P is equal to 8. The null hypothesis, P is equal to 0.1. The alternative hypothesis, P is less than 0.1, where P is a true proportion of patients like the one in the study who would experience nausea when taking the new Alzheimer's drug. So we mentioned that the power of a test to detect P is equal to 0.8 using a random sample of 300 patients and a significance level of alpha 0.5 is 0.29. So using P is 0.8, a sample of 300, and a significance level of 0.05, the power is 0.29. So they asked determine whether each of the following changes would increase or decrease the power of a test and explain. So increasing our alpha value, 0.1 to 0.05, decreases the power. Making the p-values a bigger difference. So this will increase the power because it is easier to detect a bigger difference between the null and the alternative parameter value. And C, increasing the number in the sample will decrease the power. So a smaller sample size gives less information about the true proportion of P. So I'll put that back up for a second. I want to pause it and see. And that kind of wraps it up for today. So you should be able to state and check the random condition, the 10% and the large counts for significance testing, calculate the standardized test statistic, which is our z-score, and the p-value, which is the probability of getting a z-score or more extreme, and then perform a test statistic using the state, plan, do, conclude, and then interpret the power of a significance test and describe the factors that kind of affect